Today we will be looking at an optimization problem. The problem is as follows. Luke and his uncle Owen have a gas mining farm on the desert planet Tatooine. The gases can only be farmed when the two suns that light the planet are the farthest away during the year. Sun A has an intensity of 250 lumens and Sun B has an intensity of 432 lumens, and the suns lie 10 million miles apart. Tatooine sits between them. Find the distance the Tatooine must be from each sun in order to minimize the illuminance of the two suns combined so that Luke and Owen can mine their gases safely. The illuminance E due to a light source of intensity I in lumens at a distance r in miles is given by the formula E equals I over r squared. Okay, so let's take a look at this problem, and we'll start by drawing a picture to give ourselves a little bit of context to make it easier. So we have Sun A and Sun B. We know that Tatooine lies somewhere in between those two, but we don't know the distances from each sun. We also know that the distance between Sun A and Sun B is given as 10 million miles. We are also given that the light intensity from Sun A is 250 lumens and Sun B is 432 lumens. Now let's take a look at the formula we are given. What we are trying to minimize is the total illuminance from both Sun A and Sun B, given the light intensity from Sun A and Sun B, which will be I, at unknown distances r. So what we're trying to find is these two distances right here. Well, what we can start with is the total illuminance of both of the suns, which will be 250 over r squared and 432 over r squared. But these we don't know, so we'll set those as variables. So the distance between Sun A and the planet I'll set as x, and then the distance between Sun B and the planet I'll set as 10 minus x. This will be 10 million miles minus however million miles x turns out to be, and I'll just take out the million, and then whatever answer we come up with I'll multiply that by a million. So now we have an r. For Sun A it's x, and then given the formula we square it. For Sun B it's 10 minus x, and I'll square that. Now we have a formula with which to work. What we'll do with this formula is we will set it equal to y, and then we'll take the derivative of it, set the derivative equal to 0, and then find out what the x value is when y prime equals 0. And we will do this the quick and easy way by taking the derivative of the formula with our calculator. So I will differentiate the equation and there we go. So now I will copy this, go to my y equals, and there I will paste it and graph it. Now I've already set up the domain of the graph from 0 to 10, and then y values that are conducive to showing the proper graph. So here we can clearly see that somewhere between 0 and 10, the equation does indeed cross the x-axis in the domain that we are looking for. So now to find that value of x, we find out where y equals 0, and we set our lower and upper bounds around that 0, and we are given 4.545454.5. So let's write that down. And like I said, we need to multiply this by 1 million to get the actual distance. So that will be 4,545,454.5 miles. That is the distance between Sun A and the planet. In order to get the distance from Sun B to the planet, we will simply subtract this from 10 million. So 10 minus x becomes 10 million minus our actual x, and we come up with 5,454,545.5 miles. There we go. We have found our solution, but we're not quite done yet, as we still need to prove that this is correct. And we can do this in two ways, both graphically and numerically. Graphically, we will take our original equation, plug that into our y equals and now we can see, once the graph finishes, that there is definitely a minimum that is achieved at about the same point that we found. So in order to find the exact value of that, we'll just find the minimum. And I'll go far enough to be sure that I am not missing the minimum. And once again, we come up with the exact same answer we came up with before. So, graphically, we've proven it. Now, we need to prove it numerically. What we'll do, simply plug in x values into our y equation. And we'll start with the extrema, 0 and 10. We'll put in the answer that we found. And just to be sure, we'll go a little bit below and a little bit above the answer that we had found. Let's start with the extrema. If we plug 0 into the equation, here we get 432 over 100, which equals 4.32. But that's not what concerns us. What concerns us is when we plug it in here, because we'll have 250 over 0 squared, which will be 250 over 0, which is not a real number. But what we can see from this is that it's a very large number over a very small number. And when you have that, you have infinity. Infinity plus any number is still infinity. The same thing occurs when you plug 10 in, except it occurs on this side, where you'll have 432 over 0 squared. Again, it will be a number plus infinity, which equals infinity. Now, if I plug in 4, I end up with 27.625. You'll have to believe me on that. And if I plug in 5, comes out to 27.28. Now, this y value for this x value right here must be lower than either of these in order for it our solution to be true, and it is. That is lower. We have now proven it graphically and numerically, and we have found the solution. Thank you very much. May the calculus be with you.